Now, our last part of work on permutations is the idea of what if we had those arrangements in a circle. Now, when we do something, when we consider all our other ones, we're really considering them being in a line as such. So the idea that we start with a particular spot, person in a particular spot, and then the next person follows, and the next person follows, and we're looking down that. So there's always a particular order, and someone's always at the front, and someone's always at the back. That idea, even with the words, we're rearranging the words, and again, permutations are all about order. So where the order comes into play is important. Even when we talked about the horse racing, like first, second, third, we look at the choosing first, second, third in a class, or maybe picking a class captain and a vice captain. Order mattered. That sort of thing mattered, and that was the important part. But what if we wanted to put things in a circle? It sort of changes a little bit. Now, if we want to have n objects and we want to arrange them around a circle, so for example, we're just going to do it with 3 here. So the first element A we put in somewhere. Now, because it's a circle, like there's no front, there's no beginning, there's no end of the circle as such. If you remember your Harry Potter, there's a nice little riddle about that in there in one of the Harry Potter books. It's a circle doesn't begin and end at a particular spot until we start to put an element in. So really, once we've put an element in, now we've got a beginning, but that's one element already gone in. So if we got 3 objects to go in, and we put one in there, really then the second one has one of the spots to go in. So it has a choice of 2. So, and you want to go, well, A could have been in any spot. Well, A could be in any spot, but then that just could be rotated around and become exactly the same spot as that. So, and then for the third spot, then there's only one spot to go, one place to go for C to be placed into. So when we consider something being a circular arrangement, really there's only n minus 1 factorial ways of arranging that circle, because as I said, A could have been there, but A could have been there and started there, and it doesn't really matter because we depends on how we look at it. A could be at the same spot even though it's there, and the table's just been circulated, because there's no particular order when we first place the first element in there. So hopefully that makes sense, and the idea that a circle is different to having a straight line. Straight line automatically has a position at the front, where a circle doesn't have a particular spot until you put an element in. So if we've got 6 people sitting around a table and they can sit anywhere, how many different ways we can do that? Well, we can do that 5 factorial ways. And again, you can have your people around there. But again, once you start to rotate your table, like look at your table, an idea of rotate the whole thing and the whole amount of people there, then it really becomes still the same arrangement. It's just been moved one person around. But unless the chairs are actually numbered in a particular order, then that's a little bit different, because that's actually giving them a bit more of a structure. It doesn't really matter where the first person sits. If we've got 2 people having to sit next to each other out of the 6 people this time, well, again, like consider those 2 people as one unit. So because there's 6 people and there's 5 units or 5 elements, then they can be arranged in 4 factorial ways, and the 2 people have to sit next to each other, so they can be swapped back and forwards, so they can be arranged 2 factorial ways. If we've got a circle of 20 people, 2 particular people have to sit together. Well, really, if it's 20 people, then it's 19. The idea of 19 units or 19 elements have to be arranged. So if there was in a straight line, we'd consider that as 19 factorial. Because we're in a circle, we need to consider that as 18 factorial ways that you could sit 19 elements around a circle. But again, because 2 particular people will be together, then they have to be arranged 2 factorial ways. So that's our favourable amount, 2 factorial times 18 factorial, over the total number of ways you could set 20 people around a table, which would be 19 factorial. This time Mary's to celebrate her 18th birthday by having a dinner party for herself and 11 other people. Now if Mary's to sit at the head of the table, then the other people can be arranged 11 factorial ways. So again, it's already starting to put that element in of an order, because Mary's to sit at the head of the table. So Mary can be sitting there, everybody else has to be around the table in 11 factorial ways. So hopefully you can see that Mary establishes the order, the rest of them can be 11 factorial ways. If there's 6 men and 6 women at the party, and Mary decides to seat the men and women alternately, how many ways this can be done? Well, again, the men, because Mary's already established that she has to be at the top of the head of the table, there's 6 factorial ways the men can be arranged, and then 5 factorial ways the women can be arranged. This time we've got table 4 boys and 4 girls sitting around it. Find the number of ways possible if the boys and girls can sit anywhere. Well, again, if they can sit anywhere, there's 7 factorial ways of doing that. And 2 girls have to sit together. Again, they get counted as one element. So there's 6 elements altogether for that. So they can be arranged. And that actually should be arranged 5 factorial ways. So we need to change that. So change those calculations around. So because if there's 6 elements there, oh sorry, no, that was right. There's 7. There's 8 to start off with. Sorry, there's 8 to start off with. I was thinking 7 to start off with. If there's 8 to start off with, then they can be treated as 7 elements, which 6 can be arranged 6 factorial ways. They swap around 2 factorial ways there over the total number of 7 factorial, which is the number of ways they can be arranged. All the boys have to sit together. Well, again, they can be arranged 4 factorial ways. The girls have to be arranged 4 factorial ways over the total number of 7 factorial. Now, this time we've got 9 beads. So this one is a little bit harder again. Imagine 9 beads if they're arranged randomly in a line. Well, how many ways can that happen? Well, they can be arranged 9 factorial ways. Now, if those beads are placed in a circle, how can this be done? So, well, if that's going to be placed in a circle, we know that 1 has to be put in to establish a beginning, and then they rotate, they go around in a circle, so it'd be 8 factorial ways that can be done. Now, if they're arranged on a bracelet, now this is where it starts to get a little bit harder to think about. So if you imagine a bracelet situation, when you look at a bracelet, that could be it's basically a bracelet is a circle. So we've got our circle there. We've established our first element there, and then the other ones have been looked at and been placed in the other direction. So you can have all these other elements placed around there and put around. But now with a bracelet though, when we consider this idea, a bracelet or a key ring or something like that, how can you, if you looked at it from one direction but then turned around and looked at it the other direction there, so imagine we've turned it around and we're looking the other direction, so it starts to look a bit like that when we start to rearrange it. Really, if I had all these other put this arrangement, and at some stage that arrangement would happen around here as well, but I'm already seeing that really when you turn a bracelet over, you are getting you're getting the same look but at a different side, which is basically saying, well, that arrangement has already occurred. So the idea of a bracelet is what we will need to do is divide it by 2, because we're seeing the same thing twice. So basically what we'd have organised on this side and then swap it around would already be seen if we're looking at the other direction rather than looking at this from this direction. So when we see an idea of a bracelet type of arrangement, or the other one's a key ring we often see, so we get our arrangement such it would be in a circle, so the 9 elements in a circle, and then we would divide that by 2 every time. So just be aware if you see that situation, is that's what happens with that type of arrangement there. And then, so the idea here, 12 differently coloured beads arranged around a necklace. How many different arrangements? So when you see the idea of a necklace, a bracelet, key ring, as I said, 12 different coloured beads. Okay, and they're differently coloured beads, so they're not the same. So that means they're individual elements. Can be arranged 11 factorial ways, but because in a bracelet we can look at it both ways, from both sides, that means we can divide it by 2. So just be wary of when you see that in a question, is that we're going to divide it by 2 to do those problems every time.